Hey everybody, and welcome back to World War II Submarine History with Haiku. Today's topic is U-boat underwater endurance. Our book references today are Submarines of World War II, The Design, Development, and Operations by Erminio Bagnasco, and The U-Boat, The Evolution and Technical History of German Submarines by Eberhard Rosler. And of course, our online references are uboat.net and uboatarchive.net. So your U-boat has just pulled off an incredibly daring convoy attack, and now the escorts are bearing down on you, so it's time to dive. But every time you dive, you're living on borrowed time, where power, oxygen, and carbon dioxide must be managed for the anticipated time underwater. So can you stay long enough underwater to shake your pursuit? This is the problem with being underwater. And for the purposes of this brief, we're talking about the pre-snorkel period of World War II. So this is your problem. You're in an airtight cylinder with a fixed volume of air. You can't manufacture oxygen. You have a limited ability to remove carbon dioxide, and your batteries have finite life. In this chart, you can see on the left, this is the air quality of the U-boat when you initially dive, and it's the quality and composition is equal to atmospheric. On the right-hand side, this shows what happens every time you exhale. Every time you exhale, you're taking oxygen out of the environment and you're adding carbon dioxide to the environment. Now for O2, we can actually calculate the time to reach a critical concentration inside an enclosed space, which is essentially what a U-boat is. And for the purposes of this brief, we're going to use a Type 7C U-boat as the example, and it has an interior volume of 400 meters cubed. Oxygen can be added to the interior of the boat by use of compressed oxygen bottles that are located throughout the boat and are connected to the ventilation system. And here we have a schematic from one of the technical German documents on the uboatarchive.net website. This is a schematic version of the interior of the boat. You can kind of see each of the compartments is represented, and you'll see those little bottles along the bottom. Those are your oxygen bottles that are connected to the ventilation system and spread out throughout the boat, which you would want because of the compartmentalization of the boat. You want to make sure that you can evenly distribute your oxygen. Now, like for oxygen, with regards to carbon dioxide, we can also do a calculation to determine the time to reach a critical point based on the interior volume of our space. And the carbon dioxide removal process goes like this. We have sodium hydroxide that comes into contact with carbon dioxide, and that converts the carbon dioxide to sodium carbonate and water. And CO2 is removed from the interior of a boat by the use of sodium hydroxide cartridges that can be manually inserted into the ventilation system throughout the boat. With the ventilation blowers running, moving the air through the boat, we will ensure that eventually all the air in the boat will move through these cartridges. Now, for the batteries, and this is also from a German technical document on uboatarchive.net. and this relates again to the Type 7C U-boat. On the left-hand side, inside that red box, that represents the duration of the batteries depending on the amperage that we're pulling from the batteries. Now this German document, it didn't necessarily spell this out in black and white, but I'm going on the assumption that when we're drawing the 3,630 amps, we are underwater and we're moving at maximum speed. And you can see we only have an hour and a half duration. And I believe what this chart is telling us is we continually reduce power to the e-motor, we extend the life of the batteries. The line that we're interested is on the bottom, and that's 196 amps, giving us a 50-hour battery life. And I'm going on the assumption that at that 196 amp draw, we're running the boat at 2 knots underwater, which would probably be the minimum speed you would want to go because you have to maintain positive control of the boat while it's underwater. Now here's a fancy chart, and I put this together using those equations in that table on battery life. So let's spend a little time on this. Let's see if I can walk you through it. Our graph along the x-axis, that's time that we're underwater, and as you can see on the left it's at time 0, and on the right it's at time 50. Likewise, our y-axis, it starts at 0 and it moves up to 100%. So the first thing we want to plot is battery life, because that's going to be our ultimately limiting value. And in this case, at time 0 we start at 100%, and then over 50 hours we move to 0% battery life. So at 50 hours being submerged, running at 2 knots, not silent running, we can be underwater for 50 hours. The second line in orange, that is our oxygen concentration inside the boat while we're underwater. And again, on the left-hand side, you can see we start at 20.9% oxygen, which is equal to what we would have in standard air. And as we remain underwater, that concentration of oxygen for a set number of people, and in this case we're going to use 46 sailors, you can see that over that 50-hour period we move from 20.9% down to 14%. And the 14% is significant because that is the concentration of oxygen at 10,000 feet. So if we were in a plane, if we were at 10,000 feet, we would either need a pressurized cabin or we would have to have oxygen. Some other things of interest on this line is that here in the United States, the Occupational Health Safety Administration, their minimum limit for oxygen in a confined space is 19.5%. So that's why you see when you're driving around town, if you see a manhole open and there's a truck and they're doing some maintenance, oftentimes you will see a hose extending down into the manhole, and what they're doing is that they're blowing surface air down there to make sure that they have enough oxygen. Now, according to U-boat doctrine, you would start bleeding in oxygen when the interior oxygen level got down to 17.5%. But something else to note is that you wouldn't necessarily have to do that. Many people live at altitudes at 10,000 feet or higher. If you spend enough time at that altitude, you actually do get used to the oxygen that you have available. The problem with the U-boat is that normally when you're underwater, you're at 1 atmosphere and your body's expecting a certain amount of oxygen. So as you spend time underwater and that oxygen goes down, you will start seeing some effects. The third line, that is our increasing carbon dioxide. And on here you'll see it's I kind of had to draw in these colors. Hopefully you can still understand that line. But basically we're in the green zone until the buildup of carbon dioxide in the boat gets to 1.5%, which is around 4 hours. And it would be doctrine by German standards that you would actually make your first measurement for CO2 at 4 hours. You would do that, and then you would evaluate whether or not you need to start scrubbing carbon dioxide. Now you'll notice that between and I have the values of 5% and 8% because those are used in Silent Hunter 3. And what you can see here is that between 1.5% and 5% CO2, this is kind of a warning zone. Actually, U.S. doctrine during World War II would be that you would start scrubbing CO2 at 3%. So the Germans are a little bit more conservative. Now, having said that, it's at 5% carbon dioxide that people will start having a feeling of intoxication because of the level of the CO2. So probably something that you would have to do if you were a U-boat commander, as soon as you started your patrol, when you got to a suitable location, you'd probably want to do a dive, and you would want to do that dive with the purpose of seeing what the effects of the crew would be with regards to carbon dioxide buildup over, say, 12 hours, which should still be in the yellow, more towards the 5, but not quite there. That 12 hours is an important number because ideally we would want to stay underwater during daylight. We're most vulnerable on the surface during the day, so if we can stay under during the day, that's preferable. However, we have to make sure, because we are going to be going over 1.5% carbon dioxide, we want to make sure that the crew can handle it. And so you might do, as part of your testing, you might do a dive just to see what happens over 12 hours. Make sure you have a couple guys with Draeger sets on so that they're still getting an appropriate amount of oxygen and CO2, and they can surface the boat, in case things start to go wrong. Now, once we hit 5% carbon dioxide, we're getting into this red zone, and that red zone continues up to a value of 8% carbon dioxide, at which point people are going to start losing consciousness. And again, these are the critical times for O2 and CO2 based on 46 sailors before we bleed any oxygen or scrub any CO2. So the German technical documents at U-Boat Archive indicate that through oxygen bleeding and CO2 removal, a Type 7 U-boat with 37 sailors should be able to stay submerged for 72 hours. Now, for our example, we're using 46 sailors, so you got a choice. You either got to add, and I'm guessing, but I think this is correct. You either have to add 20% more sodium hydroxide cartridges to your supply to compensate for the additional people, or you have to expect that your submergence time to decrease 20%. So instead of 72 hours with 37 sailors, maybe 58 hours with 46. So how do we monitor oxygen and CO2 inside the boat? At that time, they had two ways of making air quality measurements. One would be with an ORSAT apparatus, and you can see it's got some tubes. Each one of those tubes is packed with a specific kind of chemical that reacts with a particular component in the air. This was probably used at the 4-hour mark by the medic on the U-boat. I consider this a health and safety thing, so your medics probably has the training to do this. So he would use that ORSAT apparatus to pass a volume of air through the tubes, and he would look at the color change in each of those tubes for each of the different components of air, and he would make a determination if they were at 1.5% or not, which would normally trigger CO2 scrubbing with the sodium hydroxide cartridges. But the ORSAT apparatus probably is a little bit cumbersome to use frequently. So in addition to that, they would have had these things called sampling tubes, and they're, for our brief here, they're made by a company called Draeger, which is actually still in business. And in my civilian work, I actually come across applications for their sampling tubes with certain kinds of gases. Now, this picture of this Draeger sampling tube, this is a modern picture, but it's still the same principle. That's a hand pump with a bellows with a counter. So you squeeze it a certain number of times, you pass a certain volume of air through the tube, there's a color change, there are graduations on that tube, and you can read and you can see what would be like, say, the concentration of CO2 inside the boat. And you would have to do this probably on a schedule while you were underwater after 4 hours, maybe every 30 minutes, maybe every hour, and then you would have to make adjustments to the amount of air that you're bleeding in from those compressed oxygen bottles and the number of sodium hydroxide cartridges that you're using to remove CO2. So our conclusions. At slow underwater speed, and again, we're talking about 2 knots, carbon dioxide is the limiting factor for you staying underwater. Anytime you go above anything other than slow speed, your battery life is going to be the limiting factor. Your first 4 hours underwater are free. It would be possible to stay underwater up to 12 hours without CO2 removal, but again, as a captain, you would have to have confidence that your crew could handle that. Staying underwater longer than 12 hours, up to 24 hours, it's definitely doable with CO2 removal. And above 24 hours, you would probably have to bleed oxygen along with removing the CO2. And at 40, and even though the chart said we can be underwater for 50 hours at minimal power consumption, I'm just going to assume that you'd want to have a 10% battery reserve. So we're going to say our underwater endurance is going to top out actually at 45 hours. So how does this compare to Silent Hunter 3? I ran some tests with the game, and what I found is that if you're running at 2 knots submerged and you're not silent running, you'll hit 5% CO2 and a 20% battery life at 21.5 hours. For that same boat, under silent running conditions, you would hit the 8% CO2 level and 30% battery at 34 hours. And 8% CO2 seems to be a hard limit in the game. And as far as I can tell, the game does not appear to model the use of the oxygen bleeding and CO2 removal. So that's what you got. So the question becomes, can a U-boat really stay underwater for 72 hours, as the German technical documents indicate? Well, if the boat was resting on the bottom, and the only power draw were systems absolutely critical to the boat, which would include the ventilation system, because we have to keep the air moving if we want to remove the carbon dioxide. It's possible that you could do it. It's possible, but it's likely that you would be consuming all your sodium hydroxide cartridges to do it. So it's going to be a one-time deal. And that's why, as the war progresses, the Allies understand this kind of like hard limit with U-boats and how long they can be underwater, so they adopt this doctrine, when possible, to stay on top of a submarine contact for up to 72 hours. Because you know at that point, the submarine's probably going to have to surface. So that's it for today. Thanks for watching. Feel free to email me, follow me on Twitter. I am on Discord, and I also have a Patreon. Everybody have a great day, and I'll look forward to seeing you for the next brief.